in our last lesson, we looked at a means of determining the gradient at a point of a curve. And we did this, if we look at the diagram here, by taking a neighbouring point Q, which is quite close, so that its coordinates then would be x plus h. That's it there. Therefore, the corresponding ordinate value then is f of x plus h. So that when we work out rise over run, we came up with the expression here that the gradient of the sectant PQ is equal to this expression. Now, what we then went on to say was that if we bring Q closer to P, in other words, we're making h smaller and smaller, so eventually we saw that as h approaches 0, the gradient of the sectant was becoming closer and closer to that of the actual gradient at Q. So the expression we came up then with was the limit of this sectant was actually equal then to the gradient at the point. Now this is also called the gradient function or the derived function, and it's also known as the derivative. So the gradient function, derivative or whatever, or derived function, is equal to the limit as f of x plus h minus f of x over h approaches 0. And this process of using this formula is called finding the derivative by first principles. Now, there are actually two ways of representing the derivative. If we're using function, then we use, say, function f dash of x or d by dx of f of x. Whereas if we're using y, when we say we're finding the derivative of the gradient function, then we say we take the y dx. But for now, I'm just going to use the notation f dash of x. So if we take this example here, just to recap on what we did last week. So if we want to find the derivative from first principles, we start off by, we have to use f of x minus f of x over h. So to work out then f of x plus h, we simply replace x with x plus h in each expression. Then when we subtract, we've got the two expressions. This part here is f of x plus h minus f of x. So when we expand, then we get that, and that simplifies then to 2xh plus h squared minus 2h. So taking a factor of h out, and then when we divide by h, that expression then is going to simplify to, we'll get down to here in a moment, to 2x plus h. And of course then as h approaches 0, you can see that the expression left is going to be 2x minus 2. So we say then that the derivative of f of x using first principles is 2x minus 2. As I said to some of you last week, you'll probably be able to start to see a pattern emerging between the actual function and its derivative. Now, to answer the second question, we want to know what the gradient is at the point negative 1, 3. Now we know what the gradient function is now, so all we have to do is simply substitute in the value of x equal to negative 1, and we see that the gradient then is negative 4. And finally, the last part there says, when is the gradient 0? So what we're trying to do is find when the derivative is 0. So we put the gradient function, the derivative, equal to 0, solve for x, and we see that when x is equal to 1, the gradient is equal to 0. So this would actually correspond to, because it's a parabola up here, this would actually correspond to the actual turning point, the local minimum. So if x is equal to 1, substituting 1 into the formula would give us 1 squared minus 2 times 1. So therefore, the gradient is 0 at the point 1, negative 1. Now, if we summarise what we've seen last week and to some extent now, if we look at this table here, and I'm going to ask you just to pause the recording at this stage to see if you can see an actual pattern. So you can see that when the function is x to the 4, its derivative is 4x cubed. When it's x cubed, the derivative is 3x squared, and so on. So just pause it if you're not sure for the moment, and then see if you can write down a pattern. Okay, so hopefully you've had a look now, and you should be able to see that whatever the power is, when you find the derivative, the power comes down in front of the x, and then you subtract 1 from the power. So if the function is x to the n, the derivative then, the gradient function, is equal to nx to the n minus 1. In fact, we can take that a step further. If it's multiplied by a constant, then the derivative is just n times the constant, then n minus 1. Of course, if the function's equal to a constant, that would mean you've got a horizontal line. And of course, the horizontal line has 0 gradient. So therefore, the derivative of a constant is always going to be 0. And if you have a function which is made up of individual functions, then the derivative then is simply obtained by finding the two individual derivatives, which we'll have a look now with an example. So if we look at these here, if we've got, say, y equal to x to the 8, now because we're using y, in this case, its derivative we would express as the y. Okay, just fixing up a typo there. So if our original function is 3x squared, then finding the derivative, we leave the 3 out the front, and then inside the brackets we have the derivative of x squared, which brings the 2 down, subtract 1 from the power. You'd have then x to the power of 1, which of course is x, and 2 3s are 6. The next one, we have the sum of two parts, so we simply find the derivative of each part. So the first one, it's x to the power of 1, so it's going to be 7 times 1. Then we've got subtract 1 from the power, which gives us x to the naught, and of course x to the naught is 1, and the derivative of a constant we said before is 0. So the answer then is 7 times x to the naught, which of course is 7. If you think about it, that's the equation of a straight line. It's in the form of mx plus c, and of course the m, which is the coefficient of x, is the gradient. For a straight line, the gradient is always constant. And finally, the last one, we have 3 parts to find the derivative. So taking the first part, looks like there doesn't really matter the order we put the 5 and the 2 because multiplication is commutative. So we've got 5 times 2x to the power of 5 minus 1. Then we've got 2 times 3/5 times x, subtract 1 from the x. And of course 1 times 6x and then subtract 1 from the power. So we've got then 2 5s are 10x to the 4. This will be 2 3s are 6 over 5, and it's x to the power of 1, which is of course x. And x to the power of 0 then is 0. So that simplifies then that the derivative is 10x to the 4 plus 6 over 5x minus 6. So that means we're now ready to do exercise 9b. So in class tomorrow, I'll do a couple more examples of this just to refresh your memory, and then you'll work through those examples.